Today, we're going to look at the perceptron, one of the earliest ideas in artificial intelligence. The perceptron was inspired by the human brain, but simplified into math that computers can do. From this, we'll build up to more complex models like RNNs and CNNs. Before we look at the details of the perceptron, let's take a step back. You may remember the equation of a line, y equals mx plus b. And it looks like this when graphed, a straight line that splits things into two sides. And in this case, we'll be thinking of a yes and a no side. You'll have points above the line and points below the line, right? Now, think we put that idea into a black box. The black box takes some inputs, in this case, your x and y values, and then compares them against the line, seeing what side of the line it's on, and then outputs the yes or the no, depending on it. This is essentially what a perceptron is. It takes inputs, does some math, and then makes a simple decision. Here's the simplest depiction of a perceptron. Two inputs into the black box, which then outputs a yes or no, depending on which side of the line those inputs are on. But how does this actually work? Well, first, let's think about something more familiar, our brains. They have billions of neurons. Each one is pretty simple. It just takes signals in, adds them up, and decides whether to pass that signal along to the next neuron or not. So scientists asked, what if we built a super simplified version of that for computers? And that's how the perceptron was made. Looking at the diagram, here's how it works. First, we start with inputs. Each input has a number called a weight, which is really just how important that input is. Or you can think of it as the m number in the y equals mx plus b, what the input gets multiplied by. Then all of the inputs multiplied by their weights get added together, plus a little extra number called bias. That's the b in the equation. Then finally comes the threshold rule. If the total of the weighted sum plus the bias is enough, the perceptron outputs a yes, or if not, it outputs a no. So the perceptron is just like a tiny decision maker. The weights m set the slope, and the bias b shifts the line up or down. And the perceptron uses that line to separate things on one side versus the other to get that yes or no. Let's look at an actual example of how a perceptron would work in real life. Imagine you're deciding if you want to buy ice cream or not. In this case, the things you might be considering are, 1, is it hot outside? 2, do I have money? And maybe 3, do I even want ice cream right now? And let's say we rate these questions on a scale from 1 to 10, 1 being it's freezing cold and 10 being it's super hot, for example. Then for the weights, you need to think about how important each one is for you. Let's say being hot is, 1x important, and then having money is 2x important, and wanting ice cream is 3x. Then the bias, -10 in this case, you can think of the negative bias as making it harder to say yes unless the inputs are big enough. Okay, there's a big enough factor to make you want to get ice cream. Finally, our threshold is the same. Anything above 0 means yes, and anything below means no. Each input gets multiplied by its weights, added together, plus the bias, and if the total passes the threshold, we get the output. In this case, we get 2 times 1 plus 3 times 2 plus 10 times 3, which is 38, and then subtract the 10 to get 28, and yes, 28 is greater than 0, so we get yes as our output. This is cool and all, but you might be thinking, this doesn't actually look like intelligence. That's because so far we've only been looking at a single perceptron, which is like one tiny decision maker. But what happens if we connect a bunch of perceptrons together, like our brains? Well, here's how combining them works. One perceptron can only separate things with a straight line, right? As we saw, the yes or no. But if you connect multiple perceptrons together into layers, they can work together to separate much more complex patterns. And this is what's called a neural network. You can think of it like building with Legos. One brick alone can't do much, but when you connect a lot together, you can build bigger things like houses. So right here is the simplest version of a neural network. We have 3 inputs and 1 output. However, instead of just 1 perceptron, we have 2 that combine their outputs into a single one in the end to put in the threshold. Notice how each perceptron takes the same 3 inputs. Also notice how each perceptron has its own set of weights and its own bias. In the same way, combining perceptrons allows the network to deal with much harder problems, like recognizing handwriting, faces, or even predicting your next word in text, something that, if you remember, might sound a little bit like what ChatGPT can do. But you can make neural networks as small or as big as you'd like. Here's an example of a bigger one. We start with 3 inputs, just like the past one, but now there are 2 quote-unquote hidden layers of perceptrons. These are just the layers that are in between the input and output. They're called hidden because you never really see them in action. And each layer passes its output to the next one. So hidden layer 1 passes its output to the hidden layer 2. And finally, at the end, this is kind of new, we have 2 outputs, which is totally fine. You can have as many inputs and as many outputs as you want. So you can think about one of those outputs as, do I want ice cream, yes or no, and the other one being, choose a flavor, chocolate or vanilla. So the small network can handle a simple yes-no decision, and a bigger one can make multiple decisions at a time. Here's an example of why combining the perceptrons are useful. On the left side, you can see the 2 simple groups of points. A single perceptron can separate them with a straight line, right? But not every problem is like that. Look at the example on the right. Here, the yes group of points is in the middle, surrounded by the no group of points. No straight line can separate them. So on the right, by stacking multiple layers of perceptrons, the neural network can curve around the boundary to form more complex shapes. Okay, so now you've seen what a perceptron is and how they are combined to solve more complex problems. But remember the weights and biases each perceptron uses? You may have thought, well, how does it know what those values should be to actually give the correct output? How does it learn? Well, the perceptron first sets those weights and biases to random numbers. And at first, it might get things wrong. It might predict things wrongly. Maybe it says yes when the right answer is no, or no when the right answer is yes. But each wrong guess gives a kind of penalty, which we call the cost. The perceptron will then adjust its weights and biases by a little to try to reduce the cost. If it's still wrong, it adjusts them again and again until it gets it right. Like you can think about it like throwing darts at a dartboard. Maybe you miss the target by a lot, but after each throw you correct your aim a little bit until you get closer and closer to the center. And mathematically, this cost can be plotted as a cost function, what you're seeing on the screen here. And it looks a little bit like a hill or an upside down hill. And the goal is to find the lowest point on the hill, or the lowest cost, which means least wrong answers. And so once it reaches the bottom, it's found the best possible weights and biases to use. You can see in the visualization, it starts with its randomized weights and biases up there and slowly travels down the hill to get more optimized and, weights and biases that give more correct answers. Now we have defined the core of what a perceptron is, how it learns, and even how they are combined. However, there are more than just than one way to combine them. Simple networks are great for solving fixed problems, where you can make a decision from all the information at once, like deciding if I should get ice cream or not. But what if you need some sort of memory? That's where recurrent neural networks, or RNNs, come in. They are designed to handle sequences like text, music, or speech. An RNN is like a normal neural network you saw before, but with a loop that lets it carry information forward. Think about if you wanted to detect the meaning of a sentence, was overall negative or positive. And this requires using all words in that sentence. However, in a regular neural network, you can only give one word at a time to each perceptron. In order to retain the information about the sentence, this is how it does it. So word 1 is put into this perceptron network, right? And word 1 is represented by these 3 inputs. So multiple inputs represent this word 1. And then that perceptron network generates some memory in addition to its own yes/no output. But in this case, we don't care about the yes or no output by word 1. So then it goes on to process the next second word, or the last one in this case. And it uses the same perceptron network. However, instead of just using the inputs from word 2 now, it also uses the memory input from the previous calculations for word 1. And then it generates its yes or no output. And if it's the last word, it will just generate the yes or no output, which is this negative or positive. But you could have this chain go as long as you want, with maybe 100 different words, and each word passes memory on until you get the last one. So far, we've seen perceptrons and neural networks can handle the fixed problems, and RNNs can handle sequences of stuff, but what about images? Well, because these things, CNNs, are a bit out of scope, I'm going to provide just a brief overview of how they work. So images are harder. A lot of, think of a photo of a cat. It can have millions of pixels. If we tried to feed every pixel directly into a regular neural network, it would be way too slow and complex. This is where the convolutional neural network, or CNN, comes in. Instead of looking at every pixel individually, these CNNs use filters, small windows that slide across an image. These filters detect simple features like edges or corners. In the first layer, the CNN learns very basic shapes, maybe a line or a curve. And in the middle layers, it starts combining those into bigger things, like identifying an ear, an eye, or whiskers for a cat. And in the later layers, it puts everything together to recognize the whole object. CNNs are so powerful because they can take the vast detail of an image and analyze it step by step, from simple patterns all the way to complex patterns, without having to deal with that 4 million pixels all at once. So to conclude, today we saw, with inspiration from the brain, the perceptron was created, and then how combining perceptrons give us these more powerful neural networks, and then we explored how you can also use RNNs to solve memory problems, and then CNNs to solve image problems. And each of these steps gets us closer to building AI that can fully understand the world. Thanks for watching.